Okay. Hello, everybody. In this lecture, I am going to discuss with you how to optimize a convex function with two variables x and y in the form z equal to x squared plus y squared. We shall optimize this function in two ways. Firstly, by using the method BFGS, which is included in minimize function of Scipy, of Python, and the other way by using LabVIEW. We shall also draw this function and learn different specific modifications to draw and rotate this function by using matplotlib of Python and also by using LabVIEW graph or 3D graph. So let us begin with the Python option. At first, we shall import the required libraries or methods or functions. We import NumPy as NP. Some people pronounce it as NumPy, numerical Python. It doesn't matter. Then we import from Scipy the optimize package, and from it we call the optimize package, and from it we import the minimize function. By using the NumPy, we call the random function and import the rand function also. Rand generates an array of a given shape, array of values, which is normally distributed between the range 0 and 1. Of course, if you desire to have the values more than the range between 0 and 1, you can multiply the generated array by the given scaling value. In our case, because we are going to work with a two-variable function, x and y, so we are going to generate an array of two elements only. One element represents the x dimension and the other generated value represents the y dimension. Generally, we can express our function, the objective function, as a function of x, and we return the, let me say, x of 0 squared, or x with 0 index squared, plus x with 1 index squared. This expression is for a convex function of two variables, x of 0 and x with index 1. You can really express this function also by assigning x with index 0 to a variable called x, small x, and assigning x with index 1 to another variable called y, And then you can write that the function should return x squared plus y squared. It is the same. Both of them are acceptable and give the same result. We have to define a range of the domain of values which we are going to work with between -5 and 5. Range minimum is assigned a value -5, and range maximum or R maximum is assigned a value 5. Now we shall use our function rand with a dimension 2, which means we are going to generate two values within the array. And in order to scale these values, we multiply them with the range R maximum minus R minimum, and we add to them the value of R minimum. This gives you at the end two values which are generated randomly and express the initial position of x and y of a point. This point, which is going to be one point of the surface of our function. So if we print the point pt, we shall get, for example, here I have shown it, these values -4.6 with an exponent of -3, and the other point will be -3.86 only. These are randomly selected values. Of course, you can assign any two values. It depends, but for generality, we are assigning randomly generated point, which represents the initial value or the start value of iteration within the Scipy BFG method, minimize function. Yes. If you consider the minimize function, here it is given for you for your knowledge. It includes many different arguments, but the most important for us now is the function itself, the name of the function, the value of the starting point, and the method which we are going to use, which is BFGS here. Other values like Jacobian or Hessian, or let me say the bounds, our function is not bounded or constrained. So we are not going to use other variables within the syntax of the minimize function. So we call the minimize function, we have already called the minimize function from optimize, and we now pass the argument objective, which represents our function. This is the name of our function here. This is the name objective. So now it is passed to the minimize function, and pt is the point which we have already generated. So both of them now are defined to the function minimize, and now we add to that method, and we assign to the method here, you remember, BFGS. This is the method which we are going to work with, BFGS between two primes. So now here all the elements or the parameters are given to the function, and the function will give you an output. We assign this output to a variable we call it result. Of course, you can call it any name you want. You can write here, instead of result, answer, or a name or another name or whatever you want. But when you print this result, the function here, minimize, will give you a set of information, standard set of information, which is already decided for minimize function. So if we write print result, as I have done here, print optimization result, comma result, this result. So now this result, which is our variable here, will show this information, optimization result. You will get a message telling you that optimization terminated successfully. The success as a logic is true. The value, the minimum value of the function, func fun here, is the minimum value is equal to this number multiplied by e to the power of minus 12, which means the value of the function is 0 practically. X here is the coordinates of the minimum point where minimum occurs. The coordinates of the value of x and y, this is x and this is y values of the minimum point. It is shown x, this is by the program. I didn't write it. It is through the design of the minimize function. And also it gives you an information about number of iterations, NIT, the Jacobian, the Hessian, inverted, number of events, number of Jacobian events, and so on. So, of course, what we are here interested in is the coordinates of the point, which are shown here, 1.1 multiplied by e to the order minus 0.6, which is 0, and the other y value, which is 0. So the x value is 0. This is the coordinates of the point where minimum occurs. So this is a 0 value, and the y value is also 0. And the value of the function itself, func, I have shown it to you here, is also 0. So we have 3 0 values describing the minimum case, the minimum point, and the value of the function at minimum of the function y or z equal x squared plus y squared. Of course, you may not ask the program to print the result as it is. You may be interested with some of the elements included within the results, as I have done here. For example, I asked to print the result and I extract from it, or I slice from it, the message which is optimization terminated successfully. So when I print this, it will give me this information here, optimization terminated successfully, exactly as it gave it to me there when I typed the result of the optimization process. Really, maybe you need that, but sometimes you need also to know only about the value of the coordinates of the point. You assign or you extract or slice from the result only the value of x, and you assign it to a variable called solution. Now, if you print the value of solution, it will give you the values which were given here for x. If you ask to print the objective of solution, so this means that it will give you a value which represents the objective function for the coordinates of the minimum point where x and y are shown here in the solution. So I write, or I have assigned objective of solution, I called it evaluation. And now I can ask the program also to write for me evaluation and to write for me solution. Solution in this case gives you the coordinates of the point where minimum occurs, and the evaluation gives you the value of the function, the minimum value of the function. So again, I'm getting the same values which are supposed to be included within the result if I ask the result. Anyhow, I am just telling you these details to know that how you can manage with it, but generally you can deal only with this statement and you get all the information computed by the program. So what we get here, we found that this convex function, which is represented as a sum of squared x plus squared y, this function has a minimum where x equals 0 and y equal to 0, or x of 0, 0, and x of 1 equals 0. And the value of the function at this point also equals 0. Now, we are interested to draw this function in a three-dimensional space. To do that, because you know x and y represent a plane, the third coordinate z represents the height. So if you want to represent this function in a space, this will be a three-dimensional space. To do that, you need, first of all, to define the range of values x and y. Here, x is given given a name as a variable. It is given a name x surface, the x values of the surface, and the y values of the plane of the surface, and they are generated as two arrays, a range array with a minimum of -2 and maximum of 2, and a step value which is 0.01, 0.01. So we have generated two arrays, equal arrays, one representing the x of the surface and one is representing the y of the surface. Of course, you can write here to generate, instead of 3 to 3 or 5 to 5, any values you find appropriate. The second important thing here, when you want to draw three-dimensional figure, you need to convert the x surface and y surface, which are one-dimensional arrays. These two arrays are one-dimensional array type. You need to convert them, to convert each of them to be a two-dimensional array by using NumPy mesh grid function. So here we have called NP mesh grid function and passed to this function x surface and y surface in order to get at the output a new x surface, y surface, but this new x surface and y surface are two-dimensional. Now the height, which represents the function, which is shown as z of the surface, it is shown here as x surface squared plus y surface squared. Now, in order to draw this figure in a three-dimensional space, we need to do three things. Firstly, we need to create a figure. So from matplot library, we call from PLT figure and assign for this figure a size if we do not assign the size, the system will assign a size, appropriate size for it. It is given here 10 by 10, and that's okay. And secondly, we need to create in this figure the axis where we are going to plot the figure, and this axis must be three-dimensional. So we need to create three-dimensional axis in the figure. So from the figure here, we call the add subplot and pass to this subplot the expression projection equal or assigned 3D. By doing that, now we have created a three-dimensional space. 1, 1, 1 here represents the figure that this figure is represented or occupying one row and one column, and the last one represents the number of the figure. If you want to draw, for example, a figure which has two drawings, one of them in an array in a row, and the other of them is represented in another row. So you here to write 2. If they are going to occupy 2 columns, so this will be another 2. Anyhow, this is, you can refer to add subplot function also to know more about its details. So now we have created a three-dimensional space. We have created a figure and created axis. And now we can really plot the surface. To plot the surface from the AX we call plot surface or plot wireframe. It depends what you want. I have plotted plot wireframe, and we pass there within this syntax of the wireframe the variables which are necessary. The X of the surface, this X, the big X, and the YX, capital Y, and the Z surface. These three variables which represent X, Y, Z. Other information here passed is maybe required and maybe not required. So for example, if you want to give a specific color, here the color map, for example, is assigned a cool warm object from color map. You call from PLT color map, and from color map you call cool warm, and this will be assigned to color map of this figure. EC equal R, which means that the lines of the columns are red color. The strides here of the columns, C strides, the number of the strides, C stride equal to 5, row stride R equal to 5. Alpha is the value which represents the transparency of the color itself, opacity of the drawing. I have given it a low value so that it will be seen clearly and transparent, so that when I draw on the surface a point, the point will be seen by me. That's all. So, speaking again, from AX, I call plot wireframe, or I can call plot surface. I selected wireframe especially so that you can see through the network what is there drawn. And now, if you want to overlay the surface with a value with dimensions x and y and z, you can also draw it. So I assigned 0, 0, 0 to x, y, and z. This is the values of the optimal values which we have found above. So, and I want to use these x and y and z as a scatter plot. So from ax I call scatter, and I pass to the scatter plot x, y, and z values. And the point which represents the minimum, it is given a shape of asterisk. It is called a marker, and I have given it a color black to be seen. Here the color of the net itself, network, or the wireframe will be red. So when I have run the program, as you see, this is the shape of our figure, as you see, and this is the point of coordinates. Let me try to run it in front of you. Yes, this is the 0, 0x. This is the line. And this is the 0, 0, y. So this is the point of 0x and 0y. And this is the point which represents 0, here the 0, level of the 0 of the height. If you want to show, for example, or to overlay a point with other coordinates, of course you can do that. You can change the, for example, here instead of x equal to 0, y equal to 0, and z equal to 0, suppose I want y equal to 2. Now, and when I run the program, I shall get the z coordinate displaced. Now, this is the x of 0, and this is the y of 0, but the y is displaced up, representing that height of the, or the height coordinate, or z coordinate of the point. Here in this example, I have shown you how you can plot this function. But if you optimize these functions and you get automatically the optimum value of x and y and z, so you can directly, through the program, ask the program to plot not these coordinates, but you plot the coordinates of x optimal and y optimal and z optimal, which are z, in our case, 0 and 0 and 0, and they will be shown there also exactly at 0 and 0, 0 coordinates. In this figure here, I have plotted another plot for the same function. What is interesting here? The interesting thing I wanted to show you that here I added a statement where I called from the axis view initial function. View initial, the initial view where you show the elevation angle in degrees equal 20 and the azimuth angle is equal minus 45. So as you see here, this is the position of these angles. If I change these values, let me say from, instead of 20, I put it 45. Now we will have another orientation of the figure in the plot. Now, as you see, this different orientation. It has turned around a different angle. Suppose I want, of course, the colors also, I have changed the colors here. The lines are in green, for example. The number of stripes are different, and so on. Suppose I want to rotate this figure by the pointer an angle upon request as I want. If I try to do that, you see, it is rotating the angle which I want. Really, when working with a notebook as I do here, I am working, of course, you can turn it up and down if you want, as here. Now, the minimum is above here. And when working with the notebook, to make this occur, you need at the beginning of the program to write a specific wild character like this. 100% matplotlib notebook. This facilitates for you and makes it possible for you to rotate the figure, the angle you want. Now, also, I have managed here to draw for you another figure. Maybe you will find this more beautiful. This also could be rotated, as you see, upon request by the angle you want. And what important also that this I can save this figure. So you call from PLT save figure, and you give here the name you want. I called it mesh PNG, and now it is saved in the memory. If I want to know where it is, I go here, for example, mesh dot png must be shown. Here, mesh. Now it is given here, its position now here. If I go there to this file, I can see where it is. Here it is. Here its position. If I double click it, it will be opened upon request. Of course, it is opened by Vision Assistant software. This is from LabVIEW. Of course, you can open it by using another means. Now we shall try, for example, to open it by Paint if necessary. But Vision Assistant now will open it. It takes time to open. Now it is opened, as you see, and you can also see it in the Vision Assistant. Also, really, if we go out from here, here is our leaf. I have gone out from the program, so let me go back to it. Now I shall open the Jupyter, Jupy, Jupyter Notebook Classic, and now it will open again. Now, here is my program. Okay, so this is the program we are working with. Here's the second figure, and now we are working with the fourth figure. Here it is. I was discussing for you how we can save this figure in a file and how we can open it as we want. If we go again and try to open it with another software, not Vision Assistant, as you see, for example, mesh.png, why it is here like that? I don't know. I want here. Yes, and I go to the file there. Here it is, I told you. I can right-click it here and go to open with, here it is. Maybe with Paint, for example. Here it is also shown in Paint. Also, I have another software installed on my computer. I have noticed here that I can open it with the code. I'm not sure that it will open it or not, but the file is not displayed in the text editor. I have to display the file and then open it. Okay, not that important. So with this, we finish our work with Python. Now we shall go and do the same work which we have done just now by using LabVIEW. So we go to the folder and open the folder where LabVIEW programs, optimization with LabVIEW. And now we go, as I remember, I think it is number 7. To optimize the same function by using LabVIEW software. So we are opening now LabVIEW, and this is the front panel. I click the windows and I go to the block diagram and see, as you see, this is the program in LabVIEW. The function which is used here is called downhill simplex n-dimensional VR. This function of LabVIEW is the analog to Nilder and Mead of Python. Downhill simplex, here it is. This is the function which we are going to work with. If you double click it, or if you go to the here it is, and ask the help to show you some information about it, you will see a lot of information, but the most important thing here, you can see the input terminals which you need to use and the output terminals which are going to be shown. Yes. Here it is given that the downhill simplex algorithm, also called Nilder and Mead method, works without partial derivatives. So it depends on iterative processes and not on derivations. The downhill simplex function consists of catching the minimum of the function of x with the help of simple geometrical bodies, specifically a simplex. So what do you need to work with this function here? You need to give the start or the first initial value or the guess value of the variable. The variables which we have here, x and y, you remember. So we need to give a value for x and a value for y. And the second information here, you need to supply the program with the names of the variables x and y. And the third thing, you need to supply the expression itself, the function, which is z equal x squared plus y squared. Very simple. And then you will get at the output the minimum values of the coordinates, and the function minimum value at this coordinates. So if you go out from here, this is not now needed, we have it here. What we have done here, as you see at this point here, x, which represents the variables, here they are shown as an array x and y, These are our variables. This is the function x squared plus y squared, x multiplied by x plus y multiplied by y. You can do it this way also. And the start point here is given, for example, 2 and 2. I have tried 5 and 3, 3.12 by 3, any two values, all of them work perfectly. So when you go now to the front panel and run the add, at the output here, you will get, of course, the minimum value of the function, and you will get the coordinates of x and y. Remember, we have found them with python-Scipy, 0 and 0. X is 0 and y is 0, and the value of the function was found also 0. So now, if you go to the front panel, okay, we see, and let us run it in front of you again to see, we have found that this is 0 and 0, and this is 0. So we have found the same answer. Let us try another way, don't save. Another way of doing the same. I remember the number of the example in my folder, it was 54. This is the front panel. It is now x squared plus y squared. It is written in a different form, not as I have shown you before, but it gives you the same. So we are using the same function, downhill simplex.nD.vi. What's new? Let us see. Of course, you need to input the function. Okay, you have seen it, x squared plus y squared, the same thing. Here, this is the array which represents the variables x and y. These are empty elements which are not needed. Here, we need to input the initial guess, the value of x and the value of y, the initial values. What I have managed, I have generated an array here. Also, this array is generated randomly by using random number range VI. This exists in LabVIEW and gives you at the output a random value between these limits. So you have just to define the limits. I have given 9 and 10. Of course, you can write here -5. This is I think the start, the upper point. This is the 5. And this is, for example, -5, the lower bound. This is the upper bound. Of course, you can write -3, 3, -2, 10, 0, 12, any two values. This is a range in any way. You specify the range of values you want. You specify the variable type you need. Do you want it double precious, a number with 2 digits behind the dot, or you need it integer of 64 bits, or unsigned with 64 bits. It depends what you want. I selected double precision. How you can do that? In LabVIEW, for those who doesn't know LabVIEW, you can go to the maybe to the numerics, maybe some, I think it is there. You can find it there or not. Conversions here. And from conversions, you can select what you want. I selected this, the double precision float number. So the output here now is generated. From where this function comes, this function is included in the numbers also here. Here it is random number. If you also put it here and go to the help, you can see also what I have discussed with you, that it has an upper bound value, a lower bound value. The most maximum value it can give as output 100, the lower value is 0, but you can select any two values between them. This is the most important, and you will get the number here randomly. Okay, so here, now this array is generated. I will get only two values, one of them for X and one of them for Y. And they are selected randomly. One of them is 9.6 and 9.3. This is the lower, this is the highest. And when I run the program, I got 0, 0, and 0, 0. If I run the program again, this is another two random values. They are different, but I get the same answer. If I run again, I have another two, but all of them are between 9 and 10. If I want to change the range, okay, no problem. I can here write instead of 9, 7, for example. And if I run the program now, if I go to the front panel and I run the program, I have got also here 7.8, 9.6, and I have got 0, 0, and 0. So it is just to inform you how we can manage the optimization with the LabVIEW. What is left? An interesting thing is left. How we can draw the convex quadratic function like this one in LabVIEW, as we did in Python, and by using matplotlib. So let us try to see, first of all, how we do it in general. Number 63. It's really very interesting for you. Maybe you will like LabVIEW better than Python. So this is already done programs to be illustrated with you for the same function. As you see, this is the front panel, and here we have two figures already generated by LabVIEW. This is the block diagram. Remember, when we worked with Python, we used a function np mesh grid. In LabVIEW, we have an analog for that, which is create mesh grid 2.dvi, two-dimensional. You get at the output 2 dimensions. You input to the function 2 arrays, each of them 1-dimensional, and you get at the output 2 dimensions. Here is a two lines, 2 dimensions. Here 2 lines, 2 dimensions. Here x 2 dimensions. Here x y 2 dimensions. If I square x now, it will be x squared 2 dimensions, and now this is y squared 2 dimensions, and now I have to totalize them together. Now we will have x squared plus y squared in 2 dimensions. So the input are one dimensions X and Y. How it comes, how they are generated? Very easy. First of all, let me show you this function where it exists. The create mesh grid 2D. If right click here, and we go to the mathematics, and we go to interpolation and extrapolation, we will find here this function, create mesh grid 2-dimensional VI. So it exists and there is no difficulty to work with it. All what you need is to input to this function the one-dimensional arrays which you will work with. How to obtain or generate one-dimensional arrays? You remember in Python we used NP array. Array generated an arrays with a given limits. Here, as you see, we have a function in LabVIEW called ramp Pattern.vi. Ramp pattern. Like this, look how it goes up, as a line, continuously going and raising. It is like a ramp. A function with values increasing from a given point up to another point. Where it is and how it works. Okay, let us click here, and where we go to the signal processing, and we go to signal generation, and here we shall find ramp pattern. This is the ramp pattern. This is our function, which is here, there. It is the same one. Now, how it works, it generates an array here. If you let me here show the context help and put the cursor here and read what is there. Here, this is the same function which shows you the inputs and the outputs. Here you get you need to input the start point. You need to input the end point. And you need to input delta. What is delta? Delta is that value which is a step in Python which was equal to 0.1. It is the spacing between the values. Here it is called delta. At the output now you will get an array, and this array will be with values beginning from the start point and ending with this point, with a delta value spacing between the values equal to delta values. Here I have given the same values, -5 as a lower point, +5, and 5 as the delta. So I will get at the output an array now, beginning from -5 and ending with 5 with this spacing. If I go here, it begins from -5, -4.5, -4, -3.5, and goes on and on. I will not show you all of this. This will be 21 values here, because if you have -5 to 5, it will become 10. 10 divided by half will give you 20. We begin by 0, but not by 1 in LabVIEW. So we have 21 samples, 21 pieces, 21 intervals. So here we have 21 values beginning from -5 to 5 with this spacing, and this is our generated array. If you want any array, another array with the same values as we did in Python, we just take a branch of it and assign it to the input and assign the first one to the other input. If you want to give different inputs, you can scale any of them by multiplying a given value. If you do not want to do that and you want a completely different array, you can use another plot. You can generate another ramp from another value and put it at the input here. So it depends what do you want. So we have generated X and Y. Here they are. This is now, this is X and Y. Here the X squared, Y squared, they are summed together and they are input to plot surface. What is this plot surface? This is here. When you right click on the front panel, you will find a graph. You go to the 3-dimensional graph. And then you go to the surface, you want to draw on a surface. Go to a surface graph and press it and put it here. Here is the 3-dimensional graph. If you go to the block diagram, you will find it there. Here it is. Plot surface. It is the same as this one. And this is the display. So we know how it comes. All what we do then is to supply x squared plus y squared to the input here, which is the z matrix, and the x matrix and y matrix are given from here. And now if we run the program, we will get this figure here. Here's the figure. And here are the values which represent this figure. The difference between this figure and this figure is nothing except that the opacity of this figure is less than the opacity of this figure. How you can manage the opacity and the colors? You right click on it, you go to 3-dimensional graph properties, and here now if you go to the plots, you see opacity is given for this figure 0.7, while if you go to this figure, it will be lower, of course. 3D graph properties, it is 0.5, for example. So if you put it to let me say 2, for example, okay, and we run the program again, it will be more transparent and more. Yes, it is different now, more and more transparent. So now, principally, we have known how we can plot a 3-dimensional plot in a 3-dimensional space, 2-dimensional plot. Now, let me tell you another interesting thing. If you go back, you will find here that I have drawn 2 block diagrams. One of them represents the second here, the second plot, and the first one represents this plot. What is the difference there? The difference is simple, but I just wanted to show you. In LabVIEW, in Python, we use the arange function, which generates a 1-dimensional array between 5 and -5 with a given interval which is equal to 0.5, for example. So this ramp function here is the analog to NP arange, which is a function in the NumPy library that generates arrays with evenly spaced values within a defined interval. But you remember, we have worked also in Python with another function which generates the same array by using, if you remember, linspace function. In linspace function, you have also the borders, the limits between which the values reside, -5 to 5, for example, but you are given directly the number of elements of samples which are going to be there. So this interval between -5 and 5 is going to be divided to 21 samples. Of course, this is specifically done. I can here write 10 or 5 or 12, any values I want. Let me say, I'll show you now. So just here, I wanted to tell you that this function has the facility to select between realizing NP array or linspace array of Python. This is done just by clicking this arrow here. Now it is ramp by samples. If you click this sample array and select ramp by delta, you will get this case, which is above here. But because the connections and the work here is done by samples, so it shows me that there is an error, so I'll put it back to samples. I hope that it is very clear to you. Now, with this, it is okay, this is normal, but I want to give you also more details so that you can master it in a better way. So let us go and try to learn more about how to use LabVIEW really in generating three-dimensional plots. Let us go to number 63.1. What is there? Okay, continue to LabVIEW. Okay, let us go to the block diagram to see what is happening there, what we have done. We have three different programs. Look what do we have here. Here we still use the function which is the analog of mesh grid. Let us write its name here. Why it doesn't give name? Oh, yes, create mesh grid two-dimensional VI. Here it is the same, and above it is the same. All of these elements are the same as before, as we have done before. But here, the input array, which is generated by the LabVIEW and supplied to the mesh grid here, is generated by another way. We are using evaluate y equal function of x vi. This is a function built in LabVIEW. What does it require? It requires from you, if you want to draw a function, which is a function of x, it is y, a function of x, you need to define the limits at the input and the values or the steps or the samples which are between them. If you want to know how it comes, okay, let me right-click here and go to mathematics and go to scripts and formulas, and now we go to calculus. Is it there? No, not there. Okay, let me try again. So right-click here, go to mathematics, go to scripts. Yes, we go to one-dimensional and two-dimensional here. If we go to 1D and two-dimensional evaluation, now this palette includes this function, evaluate y equal function of x. What does this function do? Okay, so we go back and right-click it and go to the help and see what does it mean for us. Here it is. It has an input, the start, an input, which is the end. It has an input, which is the formula which you need to input to work with. You give an input values, you will get an output values as a function of the input. So here you need to give a formula so that you get an output. If you want y as a function of x, so how y is mapped, how x is mapped to y. So this is a formula at the input, but you may not need it in our case. So if you go back to what I have done here, I did not collect the input of, I do not want to have a formula. I want to just to use the generated array between -10 and 10 with a number of steps equal 400. Of course, it could be 200, 100, it doesn't matter. So now I have generated the array, and this array is fed twice to the inputs of the mesh grid, and I get at the output this function in green. Another way to work with it. Let us see what is going there up. Here I have myself worked out this piece of code where I have defined the minimum value -10. It is fed to this shift register. I have defined the values of steps between -10 and the upper value. And the upper value, I assumed that it is 10. So between 10 and -10, 20. 20 divided by the step dot 1 will give you 200. So here I am using 200 values as a limit for the iteration input, so that when the number of iterations is equal to 100 to 200, the loop stops, and now I get at the output here an array generated between 10 and -10 with a step equal to 0.1. Of course, I can here write 0.2 or 0.3. I can write here instead of -10 and or -4 or -20 or -5, and maybe I want the range to be between -10 and 5, for example. So the distance is 15. 15 divided by .100, this will be 150. And now after 150 values, the array will be output here, and it will give you 150 values. So here the art is how to generate the array differently. And now this array, which is generated, of course, you can see it here. It is -9.9, -9.8, because the step here is, as you have seen, the step itself is .1. Here, .1, the step. So you get 9 -9.9 after -9, then -9.8, -7, and it continues for 200 values. I didn't show you all the values here. And as a result of that, I have plotted the figure of the function. Of course, the function is x squared here plus y squared, and here x and y to the mesh grid, and then I get the output. We have now discussed another two different ways. This is the fifth way, maybe. We use the Chebyshev approximation. What does it differ? Nothing. It asks you to give an input minimum value. This is the order of the Chebyshev. You select any value you want. This is the end value 10. This is the beginning value -10, the beginning, okay? Start -10. This is the function which you need to work with. And this is the output now array. This is the array. And this array is fed to the mesh grid function and fed again to the surface plot. And the output here is also fed as a matrix, and you will get the same answer. The Chebyshev approximation also is existing here. If you go to the mathematics, I think, to the optimization, here it is, Chebyshev approximation function. And as a last word to show you about it, you go to the help, and here it is. So this formula also is not needed by you. You may not use it. You just need the value of x here, the output here, x, which is called x here, is the x value dividing start end in equidistant subintervals. So I have an array, here is an array between x, between start and end values, and the number is number of points which you have decided. Of course, if you need to find a specific value formula here, I just keep for the future lecture. I want to work on this with you to show you how we can make use of this directly to draw the three-dimensional figure or two-dimensional figure in a three-dimensional space without using the mesh grid function, just by using Chebyshev function or another way. I keep this for the coming lecture. With this lecture now, I think it is sufficient for you. I hope that this was interesting and that you have learned many good new things to work with. Hoping you the best and wishing you a happy day and goodbye. Okay.